anything that moves through air is affected by aerodynamics. If you have ever wondered how a bird flies to how fighter jets achieve supersonic speeds, today is the day to learn. Good evening, everyone. I'm Dilanmit Pereira, representing as host for the Phase 3 of the annual lecture series for the year 2022. And I warmly welcome you all for this occasion. With the prior permission of the principal, Mr. P.A.S.P. Jayalat, Senior Master of Clubs and Societies, Mr. T.D.C.P. Amaratunga, and the teacher in charge of the Aeronautics Society, Mr. W.H.A.D. Sumanga, we are going to start off this session. To conduct today's session, I invite Mr. Santhusa Ravihara, who is a theoretical knowledge instructor at Lakwin Flight Academy, commercial pilot license holder, and who was the chairman of the Royal College Aeronautics Society in 2015 and senior prefect from 2016 to 2017. We warmly welcome you, Ayya.
Thank you, Mali. Thank you, Mali. I just, before we start, just want to apologize for the delay in today's session because, things are not happening to schedule these days and got a power cut, so that's why the delay. Anyways, I won't take much of your time today since you all have a time restriction as well. I'm going to keep it as short as possible. And during the session, if you do have any questions, you can always get them there, ask and get the things clarified, right? Okay, so today we are going to talk about aerodynamics. I think I have done 2 sessions with you guys already, right? I think in the first one we have covered basics, right? In the first one we have covered the basics of how the lift is generated. So that's also a part of aerodynamics, right? So even though whether you knew it or not, that day also you did a little bit of aerodynamics, right? So I'll start. For the people who are already there, this first 1 or 2 minutes is going to be like a recap. For the ones who are not there, this is what we did the first time, right? Okay. Right. Can everyone see the screen that I'm sharing? Hope everyone can see the screen. Yeah. Okay. So, what do you mean by aerodynamics? First of all, aerodynamics is the study of moving air. Dynamics means moving, changing, and aero means air, right? So it's the study of moving air masses, right?
Examine the properties.
Right. So here, this is where I want to do a small recap on, right? So last time in the first session, I told you about this boundary layer, right? So this boundary layer is this blue lines you see, those are the airflow, that's the airflow, right? In technical terms, we call it the relative airflow, right? This is just the airflow that the aircraft is experiencing while it's flying, right? And this airflow behaves differently when they are passing over different surfaces on the air of the aircraft. Mainly, we are focused on the wing, right? And if you get a cutaway section of the wing, this is what it's going to look like, right? And this shape is known as an aerofoil, right? This shape is known as an aerofoil. Now, depending on the aircraft type, there are different types of aerofoils, right? Every aircraft is purpose-built, right? And every aircraft is a masterpiece of compromise, right? So why do I say it's a masterpiece of compromise? Because if you try to improve something, if you try to get something to work better in an aircraft, you're always sacrificing something else on the other hand, right? So you see, I'll explain my point later on, but as I said, every aircraft is purpose-built, right? So if you take an aerobatic aircraft, right, they can go very fast, they can do very good maneuvers, but they can't lift heavy weights, right? And it's not built for passenger movement or cargo movement or anything like that. It's bad at that, right? And if you take a passenger aircraft or a cargo aircraft, they can't do big aerobatics or whatever. right? It's built to carry a lot of weight. So things like that. Always, an aircraft is a masterpiece of compromise. I'll explain that point later, right? Here we are mostly talking, first we are talking about the boundary layer, right? So boundary layer is like the first 1 or 2 millimeters of airflow that you have on top of the surface, or behind or under the surface, right? So all around the surface basically. So the diagram here, it shows a bit more thickness than 1 or 2 millimeters, but that's just for demonstration purposes. In real life, it's going to be a very thin area, right? Anyways,
between the wing surface
this boundary layer can be 2 types, right? This boundary layer can
and
be 2 types. You can have a nice laminar flow like this, right? You can have a nice laminar flow like this, and also you can have a turbulent flow like this, right? You can have a nice laminar flow like this, one after the other, plus, it's all going in a queue, right? Here it's very messy, it's very chaotic, and this is what we call turbulent flow, right? And what we usually want is the laminar flow, right? Turbulent flow is bad. It increases the drag and creates other problems. We prefer if we can have this, right?
turbulent flow.
Right. And this is what the airflow looks like over the top surface. And I explained this on the first day. You can see on the top surface, the area for the airflow to air to go, it gets smaller. When the area gets smaller, the airflow has to accelerate. And when it accelerates, it creates a low pressure here, and relative to that, there's a high pressure over here, right? And that's how you generate a lift basically. So I'm just recapping what I did on the first day, right? Before we go on to like more aerodynamic stuff. And this is nice clean laminar flow. This is what we generally want. This is what we ideally want, but later on, right, depending on certain conditions, this can turn into turbulent flow and even can get separated away from the aerofoil, right? So that's bad, and that's something that we don't want happening in the aircraft, right?
A reduction
Like this. So it can start as laminar and then turn to turbulent later on.
in the point at which it one
Right. So that's the basic recap I wanted to do, right? And after that, we'll go to what I was actually planning on doing today: aerodynamics of different aerofoils, right? So you must be wondering, some aircraft are going very fast, some aircraft are not as fast, right? Some aircraft can lift heavy weights. Let's see how all that happens, right?
the wings of an
Right.
the shape
So this shape is what we call an aerofoil. You already know that, right?
produced is termed an aerofoil.
Right. When you hear the term aerofoil, right, you generally expect a shape like this, right? Curved on the bottom, sorry, curved on the top, flat on the bottom, right? Curved on the top, flat on the bottom. This is what you normally expect as an aerofoil shape. But there are different aerofoil shapes depending on what type of an aircraft you are building, right? So, for an example, see, if you can see this one, right? If you can see this first thumbnail here, in the middle you can see the normal type of aerofoil that I was talking about, right? And then you have symmetrical aerofoils, very thin aerofoils, and then you have see, this is the normal type of aerofoil, right, that I was talking about. And then you have supercritical aerofoils like this, right? So these are very advanced stuff. This is what you generally find in most commercial aircraft. And then you have these different types of aerofoils as well, right? So we'll just go through 3 basic types, right? So you don't have to go through all these supercritical and all that. We'll just go through 3 basic types. And we'll talk about how the lift is generated on each one, and what other contributions it makes to the 4 forces in flight, right?
An aerofoil is the following: the front.
Right.
If the wing of a
So when we are talking about aerofoils, there are certain terms that we can't ignore, right? So one of them is the angle of attack, right? One of them is the angle of attack. Now, when you say angle of attack, right? When you say angle of attack, it literally means what it says, right? So angle of attack. So you have the aerofoil like this, and then you have the airflow coming and attacking the aerofoil. That's why we call it angle of attack, right? So it's the angle that the airflow hits the aerofoil, right? That's the angle of attack, and this determines how much of a lift you are generating and whether the aircraft is going to fall out of the sky or not, right? So higher the angle of attack, higher the lift you generate, but there is a maximum limit. If you exceed that maximum limit, you lose all the lift you have and you start falling down, right? That's what we call a stall, right? So if you haven't heard the term before, an aircraft stalling means you lose the lift to the aerofoil because this angle has exceeded, right? And you start falling down, right? That's what we call the stall.
In the previous lesson, if, however, the plate is presented to the
right, like this, right? So this is the airflow. In this example, they have a flat plate, not an aerofoil, but the principle still applies, right? The angle between this plate or the cone, right, and the relative airflow, this is what we call the angle of attack, and this is very crucial when you are studying aerodynamics of an aircraft.
airflow at an angle, the flow.
Right.
If we pour down,
this is what they're trying to say here is that you can feel this in your day-to-day life, right? So if you have tried putting your hand out of the vehicle, don't do this in normal vehicles, normal roads where you have a lot of traffic coming from the other side, right? But if you have tried putting your hand out, right, and then if you have felt that wind hitting on your hand, right, and that movement of air through your hand creates a force, right, which tries to take your hand back and a bit up if you have it at an angle, right? If it's just like this, it won't do much, right? You just feel the resistance, and if you try angling it a little bit, right, it hits the airflow, hits the surface here, the bottom surface here, and the hand will try to go back and up, right? The hand will try to go back and up. This is the same thing happens in an aircraft as well, right? You have the wing, right? You have the wing of the aircraft, right? If the wing is presented to the airflow at an angle, what will happen? The wing will generate a force, right? The wing will generate a force. That force will try to take the wing up and back at the same time. This upward component is what we call the lift, and this backward component is the drag, right? It's not the only drag you have, it's part of the drag that you have. We call it induced drag, right? Any questions up to this point? Okay, I take the silence as a no.
but tilting the hand slightly in the airflow generates,
Right.
producing lift efficiency.
Right. So see, this upward part we call the lift. Backward part is part of the drag that we experience, right? So the purpose of an aerofoil, right? The purpose of an aerofoil is to be as efficient as possible for its purpose, right? So what I mean by efficiency is you can see even in this flat plate. This is a flat plate, not an aerofoil shape. Even in this flat plate, you get a total reaction, you get a lifting force, and you get a drag force, right? So you don't necessarily need to have a aerofoil shape, right? If you have done model flying, when you are starting off your model flying, you might be fitting wings that are like this, right? So I'm not sure if you guys are doing model flying in the ground nowadays. During our time, we used to do a lot of model flying, right? But if you are starting off with very simple models, you are likely to use an aerofoil like this, right? So you can still fly with something like this, right? But it won't be efficient. What do I mean by efficiency here, right? Is that for a given amount of lift, right? For a given amount of lift, you produce the least possible drag, right? Or highest lift possible for a lowest drag penalty, right? So highest lift possible for the lowest amount of drag. That's what I mean by efficiency. So if a wing can produce a lot of lift compared to the drag that it generates, then we can say that aerofoil is efficient. So this is not an efficient aerofoil because this will create a lot of drag compared to the lift, right? That's where the aerofoil shape comes into play. Right here, so this is the comparison between the flat plate and aerofoil. You can see the flow characteristics. Here you can have a lot of turbulence. Here the turbulence is not that much, and you get good characteristics over here, right? So this is a more efficient aerofoil. This is a more efficient shape or wing compared to this one. That's why all aircraft tend to have some sort of an aerofoil shape, unlike your model aircraft, right? All real aircraft tend to have some sort of a aerofoil, not this type of wings, right? Any questions? No?
No, yeah.
Okay.
Increasing the angle of attack still further, this condition is
right. So as I told you, there is a particular limit where this increment of angle can take place, right? And that maximum angle is about 16 degrees, right? It's not 16 for all aircraft, it's approximately 16, right? I'm not saying that all aircraft will stall at this angle, but it's approximately 16 for any aircraft, right? Now you can ask me a question. If you have seen military aircraft, you might have seen military aircrafts doing vertical climbs like this, right? So this is a very popular question that we get even in piloting lessons, right? Even the people who are doing piloting initially, they tend to get this part confused over, right? Anyone here, do you have any idea how a fighter plane can climb like this vertically when the wing of the aircraft stalls at 16 degrees? So what I'm trying to say is, so 16 degrees is a very small angle, right? So if 16 degrees is even smaller than this, 16 degrees is a very small angle, probably smaller than this also, but you might have seen fighters climbing like this in some cases. Anyone here has an idea how this happens? Are they not stalled here yet? Sorry?
The speed is high.
The speed is high. Okay, but even though, and the other thing is, no matter what your speed is, if you exceed this angle, you will stall. So speed is not the answer.
The aerofoil shape is like two aerofoils stick together.
Okay, that's something that I was going to say later. That's what makes it go faster, right? So what you are trying to say is the aerofoil is not, it doesn't have a curvature only on the top, it has a curvature on the bottom as well, right? So that's what we are trying to say now. So that's what makes it, that's the property of the aerofoil that makes it go faster, but not this. Anyone? Any other answers?
To get into a vertical angle?
Sorry?
They use the stall to get into a vertical angle?
Oh, no. If you are stalling, what a stall mean, the meaning of a stall is you lose the lift and you start falling out of the sky. So if you stall the aircraft, you fall out of the sky. This is very dangerous for a fighter aircraft because fighter aircraft are not very stable aircraft. So once they stall, it's very hard to recover, right? So even in this type of a climb, they are not stalled yet. They still have the lift. It's actually a very simple answer, right? So what happens is, if you are climbing like this, where is the airflow coming from? Where's the airflow coming from? Ranude, I think I didn't hear you clearly.
Sorry, no.
Right. So what happens is, when you're climbing like this, right, the airflow is coming like this, right? So many people think airflow is always like this. No, the airflow is parallel and opposite to the flight path, not the aircraft, right? So here you can see diagram the diagram, the airflow is like this, in this direction, right? That's because the aircraft is traveling this way. The aircraft is traveling that way in this example, right? But in this case, the aircraft is traveling up. The airflow is coming from the top like this, right? So this angle has to be between, clearly show it, the airflow is like this, right? So this angle of attack is the angle between the chord of the wing and the airflow, not this. This is not the angle, right? The angle is this. As long as this angle is less than 16, you are fine, right? As long as this angle is 16, you are fine, right? And the fighter, usually fighter aircraft or aerobatic aircraft, they can sustain this climb because their engines are powerful enough to keep the aircraft vertical like this. Otherwise, if you do this in a normal aircraft, what will happen? Because the engine is not powerful enough, the aircraft will start slowing down, and it has to, keep doing this. It has to keep increasing its angle of attack to maintain lift, and at one point it's going to stop, right? But if you take something like a good fighter or a good aerobatic aircraft, they have a lot of power, and they can keep the aircraft going in this attitude without slowing down. That's the point, right? Not that they are stalled or anything like that. That's the point, right? So this is something that even flying students tend to get confused in most cases, right? But it's a very simple principle, right? Any questions?
No,
Okay.
yeah.
Good.
Is called the stall. From the
Right.
most aircraft do.
Right. So I told you I'll show you 3 simple aerofoil shapes, right? So here they are, right? So you can see on the top you have the high lift aerofoil, right? The high lift aerofoil is very thick, right? It's very thick. It has a very round edge here, and it has a big curvature, right? So this is a high lift aerofoil. And then you have the high speed aerofoil, right? In the high speed aerofoil, the aerofoil itself is thin, and mostly it's a neutral camber. What do I mean by neutral camber? There is no curvature. I mean, there is a curvature, but it's equal on both top and bottom, right? Or very close to being equal, right? So as I said, an aircraft is a masterpiece of compromise, right? So in this type of aerofoils, it's a high lift aerofoil, right? High lift means you can lift a lot of weight, right? You can lift a lot of weight with this type of an aerofoil, right? So yes, very good in that aspect, right? But also at the same time, with high lift, right? With high lift comes high drag also. Can you remember? Lift is always associated with drag. More lift you make, more drag you make as well, right? So that's why I said masterpiece of compromise. Nothing is free. You get some lift. The cost of having that lift is more drag, right? So even though they can lift a lot of weight, right? These are heavy lifters. They can lift a lot, but they are slow, right? They can lift a lot, but they are slow, right? And then you have the high speed ones. These are the ones that you find in fighter aircraft, aerobatic aircraft, right? These aerofoils are very fast, right? These aerofoils are very fast, and even in supersonic aircraft, you'd find something close to something that looks close to this, right? But at the same time, they are not very good lifters, right? They cannot carry a lot of weight. Have you ever seen a fighter aircraft the size of an Airbus? Have you ever seen a fighter aircraft that is the size of an Airbus?
No, yeah.
No, right? That's the reason, right? That's one of the reasons. They are very fast, they are very agile, but they can't lift a lot of weight. They rely a lot on their engine power, right? Whereas this guy, right, can lift a lot of weight, and but at the same time very slow, right? So either you can lift a lot and go slow, or go fast and lift only little, right? So those are the two extremes. And then you have the general purpose. General purpose is what you'd find in most general aircraft, right? So it's a mix of the two, right? It's not as cambered as the high lift one, not as thin as the high speed one either. So this sits in the middle. Understood?
Yes, sir.
Okay.
And high speed.
Right. So to explain the lifting ability of the aerofoil at different angles, you use a graph like this, right? So this graph, the terms might be a bit complex. So if you don't understand what this EL means, just don't think too much about it, right? So just think of this axis as the lift, right? CL means coefficient of lift for the ones who can understand the term, right? This is a part of the lift equation, right? And this for normal general purposes, you can just take this as the lift, right? So you have the lift on one axis and angle of attack on the other axis, right? So I'll take the general aerofoil first, the red line, right? So you can see, even though the aerofoil is at 0 degrees angle, even though the aerofoil is completely at a flat angle, that's here, that's the 0 angle, right? You can see it still produces some lift. It's still able to produce some lift because of the curvature of that aerofoil, right? Because of the curvature of that aerofoil, it's still able to produce some lift. Now compare that with the blue line, right? Blue line, that's the symmetrical aerofoil. The symmetrical aerofoil, if it's at a 0 angle, if it's just laying flat like this, it won't produce any lift, right? So this aircraft, this blue aerofoil cannot fly at 0 degrees angle of attack. It won't produce any lift. It needs to have some sort of a angle of attack in order to keep flying, right? Whereas the normal aerofoils, they can fly even at 0 degrees of angle of attack. For normal aerofoils, it actually becomes 0 at -4, right? -4 angle of attack. Meaning, if this is 0, you can actually point the wing down 4 degrees and still get some lift. -4 is the point where you get 0 lift. If it's a little above that, you'll get some lift there, right? So that's what they're meaning here, right? And you can see the lift keeps on increasing. When you increase the angle of attack, lift increases, right? So if I take an example, right? If I take an example for this angle of attack, this is the amount of lift you generate, right? For this angle of attack, this is the lift you generate. So if the wing is pointed up, you generate more lift, right? But it only happens until about 16 degrees here, right? You can see at 16 degrees, the graph curve peaks and starts dropping. That's the point of stall, right? That's the point of stall, right? So there you have it. That's how a wing can generate lift, right? So that's the aerodynamic of the lifting force, right? And at the stall also, you can see some differences here, right? You can see the symmetrical aerofoil is stalling faster, right? Symmetrical aerofoil, the fast aerofoils are stalling faster, whereas high lift ones, they are stalling slower, they are more gentle, they are easy to recover, right? This type of aerofoils are easy to recover. This type of aerofoil is very hard to recover. There are some fighter aircraft. In this type of aircraft, even if you don't do anything, if you stall the aircraft and even if you don't do anything, the aircraft itself might recover sometimes, right? So it's that good in that terms, right? But if you stall something like this, if you stall some fighter aircraft, the standard procedure is actually to eject. They say if you stall that aircraft, you will recover the aircraft, right? So it's a very drastic difference that you have, just depending on what type of an aerofoil that you have there, right? So why is this stalling happening in the first place? Let's do that. Right. So this is the pressure distribution around an aerofoil. You have low pressure here, somewhat low pressure here, but still compared to this area, this is a high pressure, right? And the highest pressure at the leading edge of the aerofoil, right? So that's where the airflow comes and strikes the aerofoil. That point you have the highest pressure.
The shape of the pressure
Right.
upwash was explained.
So here you have upwash and downwash, what happens here is the airflow has to bend up in order to go over the aerofoil. That's what we call upwash. Here, the airflow will go down. That's what we call the downwash, right? Just some terms that are nothing too significant at this point.
As occurring because the wing area.
Right.
Now that we can identify now with this in the pressure differential.
Who here has seen small tornadoes behind the aircraft wings?
I have seen.
Right. Ever wondered what they are or how they are created? Anyone here who knows
I think they are created by the turbulence.
What type of a turbulence?
I don't.
Anyone here who knows how they are created? No? Okay. So
modifies the direction. Now that we can the course.
Right. So what happens there is that I told you there's a high pressure. There's a high pressure under the wing here, right? So high pressure under the wing here, right? Low pressure on top of the wing, right? So high pressure always wants to go from high to low. Pressure always wants to go from high to low, right? But because the aerofoil, because the wing is there, it can't do that. What it does instead is lift the entire wing up. That's how you get the lift, right? But there are areas in the wing where it can escape this, right? So here, if you take the wingtip area, so wingtip is this area, right? So if you take that wingtip area, right, here there is some possibility for this high pressure air to jump from here to here, right? From here to here. So this motion creates a circulation pattern of air, right? So if this is the wing, it creates a small circulation pattern behind the wing, right? So this is what we see as wingtip vortices, right? So these are bad, right? These are bad. They generate a lot of turbulence. They reduce the efficiency of the wing because they drag and increases the fuel consumption. And it can be dangerous for any aircraft coming behind as well, right? So if you have a heavy aircraft, let's say you someday join a flight school and then you start training or whatever, right? You'll be using light aircraft, right? So if this light aircraft goes behind a big aircraft like a 320 or something like that, right? Then this turbulence, right? The turbulence from this big jet that's in front of you can cause a complete control loss in your aircraft, right? It's that significant, right? So for that reason, when two aircraft are approaching one after the other, there should be a gap, right? So there should be, depending on the sizes of the aircraft, that can depend, right? So there should be a gap between the leading aircraft and the trailing aircraft, right? So they can't fly very close to one another, or they'll end up in the turbulent area and they can crash even. There have been crashes that happen because of that, right? So that's how wingtip vortices are generated, basically, in layman's terms, right?
Now that we can, it must be remembered.
I'll just show some clips of wingtip vortices. This one. Right. So can everyone see the screen?
Yes. Yeah.
Okay. So now look at this. Look at all these aircraft. Pay special attention to these areas, right? In some aircraft, you can get from this area also because the flaps are extended up to that area, right? So pay attention to these wingtip areas and where the flaps are usually extended from. there. See, these are the wingtip vortices, right? These are like small tornadoes, right? They turn like this, right, opposite to one another, and that can be very dangerous if you get into one of those. And this is not, you might think that it's a very small area like this, but no, it does affect a very large area. You only see that small part in some cases. You can see the area that's affected when aircraft are flying through clouds, right? And the other thing is, have you ever wondered why some aircraft have tips like this? See,
To
here
reduce the turbulence.
to reduce the wingtip vortices, right? Not just any turbulence, to reduce the wingtip vortices, right? So even with these, you can still get those, but the effect is somewhat reduced. See, it's a very big area. This aircraft is coming off from the flaps. See, it leaves the vortex. Look at this. So even after the aircraft has passed, it leaves a big vortex for some considerable amount of time. See, this area is still turbulent. Right. Okay. So there is this very good text with video. I'll put this link on to one of you guys on the board. They can share this in their group, in your group or whatever. I won't play this because we are restricted by the time, right? Anyways, now I want to show you something else, right? So I told you an aircraft will stall, right? And stalling happens when the airflow is separated away from the aerofoil. You can actually see this happening in a real life in a smoke tunnel, right? So let me get a good video out of here. This one should be good. Yeah. So this is just a flat
Aya.
Yeah.
I have a question, Aya. So
Yeah.
what if a lightning strikes the plane?
Okay, it has nothing to do with aerofoils or aerodynamics, but I'll explain what happens. Have you heard of the term Faraday cage?
No, Aya.
So what happens is,
Unfortunately.
the aircraft just acts as a path for the lightning to pass through. Right? Have you seen small what do you call this? The term we call it is static wicks. Wait, I'll show. Have you seen this in aircraft?
Yes.
Right?
Yes, sir.
So these are called static wicks, right? So their job is to release static electricity that may build up on the aircraft into the atmosphere, right? So what happens is the aircraft is made up of conductive materials, not some sort of a metal or something like that, right? So what happens is when a lightning hits the aircraft, right? When a lightning hits the aircraft, it just passes. It hits here and just goes from this end. Right, it might cause some errors in the instruments, can cause some burning on the area where the lightning actually struck, but other than that, it's not going to bring any aircraft down. So lightning strike is a very common thing for aircraft, and it's not going to do any damages. And these static wicks are going to act as discharges. So any static electricity that builds up on the aircraft like that, they will be discharged through the static wings, right? I'll actually show a clip, small clip. See here, you can, in this screen, if you can see in this, wait, I'll play it and post it. Yeah, right. So the lightning hits the aircraft, right? So it hits here and just passes from this end. Nothing happens to the aircraft.
Okay, Ayya. Thank you, Ayya.
Right?
Aya,
Yeah.
can it pass in from the other end as well?
Sorry?
Can it pass from the other end as well?
It can pass through any end. It just passes it, whatever the least resistive path that it finds, it passes through that.
Okay.
Right? Nothing will happen to the aircraft. There might be some burn marks here, and the instruments inside the aircraft might get, you know, some errors in indications, and obviously the light of the lightning is there, so the pilots might get blinded temporarily. But other than that, it's not going to bring the aircraft down. Lightning strikes are very common in aircraft. At almost all the aircraft have at least experienced one lightning strike in their lifetime.
Aya,
Yeah.
Aya, so when like what is happens, does it also affect the engine?
No, no. Engine of the same aircraft? No.
Okay.
Right. So what I was going to show is this. The Aerofoil. Okay, so this is the. Okay, so the white lines you see here are actually smoke, right? And you can see how the smoke behaves as the angle of the aerofoil changes, right? See, angle of attack is now increasing here, right? You will see when the angle of attack is increasing, the lines here are getting close to one another, right? When they are getting close to one another, what that means is that they are getting faster. The airflow is getting faster. And also see what happens in this area, right? See what happens in this area. The airflow here, it's flowing very nicely in uniform lines. Here, over this area, as the angle increases, it gets turbulent. And at one point, it separates away from the aerofoil, right? So when it's completely separated away from the aerofoil, that's what we call the stall, right? So increasing, see, you can see it starts to get turbulent. Now it's separating. Still attached, still attached. Still attached. Now it has separated. See, in this area it has separated already. And over time, it will completely separate away, and that's what we call the stall. So you can look at it from this angle also. That's the stall. There the aircraft has stalled down.
Excuse me, Ayya.
Yeah.
So, Ayya, behind the wings, like on top of the wings,
Okay.
Where the airflow is not actually drawn. So is there like a place where no air is there?
What do you mean? Here, this area?
Yes, sir. Yeah.
It's not that there is no air. The air is not moving.
Okay.
In this area, air is not moving as in it's very slow moving or stationary, something like that.
Okay. Thank you. Yeah.
Right. See, now it gets very turbulent. At this point, it's completely stalled. Right? You can see how much of a turbulence it creates. This is compared to the flat plate. And then this is the flaps. Right? Flaps can temporarily increase the lift. See, they are both at the same angle, but look at the difference. See, and also it has become more turbulent over here. Right? So with the flaps, you get a lot of. You can increase the lift. You can see the difference here. Right? You can get a lot of lift, but also at the same time you increase the drag as well. Right. Okay. Any questions?
No, yeah.
Okay. Uh, right. So to finish off today, then I'll talk about the ground effect. Right. So
Reduced drag reduces.
right.
However,
So in red color,
when an aircraft
you can see the wingtip vortices that are generated by the aircraft. Right. So it won't be actually red color in real life, but you get the point, right? So this is the diagrammatic view of the wingtip vortices. So this is in air, right? This is in air, right? But what happens when you get close
the
to the ground?
explanation that's been given. However,
When you get close to the ground, right? These wingtip vortices, they will hit the ground and they will die down, right? Once you are getting close to the ground, the wingtip vortices will actually hit the ground and the effect will lower, right? So you can actually see this in the actual videos also.
Hey, it's Mario.
Right. So do you see any vortices now?
No.
Right. It's because the aircraft is still on the ground, right? So the wingtip vortices are not very strong enough at this point. You don't see them, right? So see what happens as soon as you get off the ground and gains a little bit of height. See, now it's getting off the ground. See what happens at the wingtips. Now you start getting them, right? So even in this landing aircraft, see what happens as soon as the aircraft touches down. See, no more wingtip vortices from there, right? So what happens there is you enter what we call the ground effect, right? What happens here is that you come, and when you are getting close enough to the ground, these wingtip vortices will hit the ground and they will get weaker, right? And this usually happens at about half the wingspan, right? This usually happens at about half the wingspan height. So let's say the wing from this tip to this tip of the wing. So if I take an aircraft like this, so from here to here, that's the wingspan, right? Half of that. So if the distance between from here to here is 20 feet, let's say for an example, but by at about 10 feet, right, you enter the ground effect, right? By at about 10 feet, you enter the ground effect, and in the ground effect, all these wingtip forces, they will hit the ground and they will, get weaker. And what it does to the aircraft is that I told you these wingtip vortices, they increase the drag of the aircraft, so reduce the performance, right? So when the aircraft comes closer to the ground, it suddenly starts flying better. You get lots of lift and you get low amounts of drag, right? Your speeds will also tend to increase, right? Your speeds will also tend to increase, and the aircraft will suddenly start performing better, right? And this is what we call ground effect. There are actually not aircraft. There are actually certain vehicles that usually use the ground effect, right? They only use the ground effect. They can only get off the ground over a certain height only, but they stay there, right? And they continue to move like that, right?
Excuse me,
yeah.
Like I have heard that there are like planes that fly just by like when there's like they like fly really near the ground, and because of the pressure between the ground and the wing, they like stay afloat.
Yeah, those are not planes only. Planes, they can fly even above that height, right? There are some vehicles, I don't want to call them planes because they are not planes. They can't actually get off that and keep flying, right? So there are some crafts, not aircrafts, crafts, right? That can actually do that and just stay hovering over that area. Let's see if I can find one. There's this Soviet Russian one, I can't remember the name.
The Caspian Sea monster.
Yeah, that's the nickname given to it. Let's see what the actual name is. Yeah, this one. It's a ground effect vehicle, not an aircraft, right? So what happens here is, yeah, see, this is the thing that you're talking about. Yes, right? Caspian Sea monster is the nickname given to this. The actual name is something else. Here, this is the actual name, some Russian name, Extremoplan. Right, this is the actual name. So what happens is, if you can see it in the images, it's not flying. See, it's not technically flying. Here, this one. It's not technically flying. It's just on this. It's just a particular height over the ground. That's it. Right. So they use the ground effect to travel, not to fly. I don't want to call it flying because you are not going away from that, right? So for this to be an aircraft, it needs to get above that and continue to climb up to a certain altitude, right? So this is not an aircraft. This is some sort of a other vehicle. I don't know the actual class of this vehicles, right? So anyways, what I was trying to say is that that's the ground effect, and when an aircraft enters that, it suddenly starts performing better, right?
An aircraft is taking off.
And
The
if you are
reduction in
not careful enough, this can happen to many student pilots who are just starting to fly. The aircraft will actually start going up again when you're coming into land, right? When you're coming to land, the aircraft will actually start going up again for a short while, right? So That's what we call the ground effect. Any questions there?
No, yeah.
Right. I actually hope I could have done a little longer, but because of the power cuts and the time restraints you have, I'll end it there, right? So, if you don't have any questions, that's it, I guess. That's all I'm going to do today.
Excuse me, Aya.
Yeah.
Talking about the previous thing, does flaps increase the stall angle or make it worse?
It's like this. When you put the flaps down, the stalling angle will decrease, right? The stalling angle will decrease, but the stalling speed is also going to decrease. So it's good speed wise, bad angle wise. But what you generally want is to have a slower speed by using the flaps. So that's what we are using flaps for, right? So I told you to explain it better. I think I can do better than that. So what happens is can you see the whiteboard?
Yes, Aya.
Right.
Yes, sir.
So what happens is my drawings on the screen are not that good. Okay, this is better, right? So let's say this aerofoil is already at 60 degrees, right? Let's say this aerofoil is already at 60 degrees. This angle is 60. When you put the flaps down, right? When you put the flaps down, the chord is like this. The angle increases, right? So what happens? You start, even though the wing is at a smaller angle, right? It thinks that it's at a higher angle than that, and it will stop, right? Even though the wing is still, let's give some numbers to this so that you understand better. Let's say the angle is 14 here, right? And you stall at 16, right? You stall at 16. The moment you put down the flap, what happens is now you have this part also. No? So you have to start the measure. You have to start measuring the angle from there. Okay, it's a little off, but you get the point. Now this angle is what you're measuring. This is more than 14. This can very well be 16 or 17. At that point, it would have been stalled. So even though the wing is at 14, you stall at that angle because the flaps are down. So angle of attack for the stall will decrease, right? You won't be able to pitch up as much as you used to do, right? But you can fly slower, right? So without the if I take the aircraft if I take the Cessna 152 aircraft, which is the basic trainer that we use, that aircraft is going to stall at about 40 knots without the flaps. And if you put the flaps down, you can actually go up to 35. You can go even slower with the flaps. So that's the purpose of flaps. You can go slower with the flaps down.
Aya,
Yeah.
have you like flown the and like අය දැන් ඔය Cessna 172 SP plane එක අය මේ පැදලා තියනවා කියන්නේ දුර ගමනක් එහෙම පැදලා තියනවද?
මම මල්ලි 152 පැදලා තියෙන 72 නේ. ඒ වුණාට දෙකේම නිකන් ප්‍රින්සිපල්ස් එකයි තියෙන්නේ. දෙකේම ෆ්ලයි කරන විදිහෙම ලොකු වෙනසක් නැහැ. එකම වෙනස ඉතින් 172 එක ටිකක් බරයි 152 එකට වඩා ඒක ටිකක් ඉඩ තියෙනවා 152 එකට වඩා. මොකක්ද ඒකෙන් අහන්නේ ප්‍රශ්නේ?
අයියා කියන්නේ දුර ගමනක් එහෙම කියලා තියෙනවද? ඒක නිකන් ලංකාව ඇතුලේ දුර ගමනක් එහෙම කියලා තියෙනවද?
ලංකාව ඇතුලේ මම ගිහිල්ලා තියෙන දුරම ගමන තමයි රත්මලානෙන් ටේක් ඔෆ් කරලා රත්මලාන, සීගිරිය, මින්නේරිය, රින්කොමලි, අනුරාධපුර, කල්පිටිය, කටුනායක, then back to රත්මලාන. ඔය ඔක්කොම එක දවසේ පැය 5ක ෆ්ලයිට් එක.
ඕකේ අයියා.
මම ගිහලා තියෙන ලොකම ෆ්ලයිට් එක.
අයියා. අයියා මේ චයිනා බේකින් එහෙම මේ ලෑන්ඩ් කරලා තියෙනවද?
ඔව්.
Okay.
Aya, are you a pilot?
Yep, sort of. Anything else?
Like, do you know the basics of a commercial aircraft?
Yes, we have to know them. That's what we learn in commercial when you study for CPL. That's what you learn.
Okay, so have you like flown one of the commercial airplanes?
I have flown the simulator, as in like the simulator on the Sri Lankan airline, the actual simulator. I have done a small flight on that. That actually was during.
And I'm sure all of us can agree that was fantastic explanation. And on that note, I would like to deliver the vote of thanks. Today's event would not have been possible without the help of some very special persons. So I would like to thank our principal, Mr. P.A.S.P. Jailat, Senior Master of Clubs and Societies, Mr. T.D.C.P. Amartunga, our teaching in charge, Mr. W.H.A.D. Sumanga, members of the Prefects Council of Royal College, and also a very special thank you goes out to our chief guest, Mr. Santhusa Ravihara, for taking time out of his schedule for sharing his valuable knowledge. And last but not least, I would like to thank everyone here for their participation today, and I hope you have a very pleasant evening. Thank you.